In our previous lecture video, we talked about why we shouldn't look at the likelihood of getting the exact sample proportion or the exact z-score that we did, assuming your null hypothesis is true. Because that likelihood is always going to be zero. There's an infinite amount of outcomes. One specific outcome will have a probability of essentially 0%. We need to find something what's called the p-value. And I'm going to put some stars around this. The p-value. What this does is it looks at the likelihood of obtaining this specific sample proportion or the specific z-score or more extreme values, assuming your null hypothesis is true. For instance, if we were to do this out, right, we received a sample proportion of 0.518 and a z-score of 1.80. But what we're going to do is not find those exact likelihoods. We're going to find more extreme outcomes as well. And what we're going to determine as more extreme is coinciding with our claim, our HA. Since we're trying to prove, or maybe not, since we're trying to support the claim that the likelihood of rolling an odd number is greater than 50%, we're going to look for the more extreme values. And what we're going to determine is the more extreme values are the values that coincide with our HA. We're trying to prove that the proportion of rolling an odd number is greater than 50%. What we're going to do is look at the likelihood of getting a sample proportion of greater than or equal to 0.518. A z-score of greater than or equal to 1.80. The more extreme values for our hypothesis test are determined by your HA claim. If we were trying to prove it was less than, we would look for all the area less than or equal to. To visualize that, I'm going to shade in that area. We're looking for all of this blue area right here. All of this blue area right here. This will be our p-value. 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 We'll be able to find that area using our distribution calculator. I've opened up our distribution calculator. We're dealing with a normal distribution, and we turned our sample proportion into a z-score. So we should be at our standardized distribution, our z-distribution. Mean 0, standard deviation is 1, which is what it does by default. We'll input the value we're interested in, 1.80, and we'll look for all the area greater than. And we see that area is 0.0359, roughly 3.59%. This is our p-value. We found the likelihood of getting that z-score or one more extreme, assuming the null's true. So let's take a look now that we have this p-value, 3.59% roughly. The area we just found is being represented by this visualization, approximately 3.59%. And that's the same area as the graph in the distribution that we're interested in, the distribution of sample proportions. Those two are the same values. If we wanted to write this out numerically, again, both of these areas represent 3.59%. And here's essentially what this is saying. There's a 3.59% chance that we would have gotten this sample proportion, 51.8%, 0.518. There's a 3.59% chance we would have gotten this sample proportion or one that is larger, right? We look for all that stuff greater than, or one that is larger if in fact there was a 50% chance of rolling an odd number. So if I gave you a fair dice, if the chance of rolling an odd number was 50%, if that is true, there is a 3.59% chance you would have gotten this sample proportion or one bigger. You can think about it in terms of a z-score. Assuming I gave you a fair dice, assuming the chance of rolling an odd number was 50%, there was a 3.59% chance you would have gotten this z-score, 1.8, or one bigger. So it was very unlikely for us to have gotten the results that we did if, in fact, I gave you a fair dice. It was very unlikely to have gotten those results if I gave you a fair dice. So maybe the thing that we should conclude then, or support, is actually I gave you a fixed dice. The question we'll be asking ourselves, though, is how much evidence do we need to say I gave you a fair or a fixed dice? Let's go check out some of these things that we learned in terms of our notes. To recap, our first step was to come up with our hypotheses test. Our second step was to find our test statistic. And we just talked about our third step, which is to find our p-value. The p-value, again, more broadly, represents the likelihood or the probability of getting the sample statistics that we did, the data we did. That's our evidence. In this case, it was our sample proportion. How likely was it for us to have gotten our sample proportion, or one more extreme, if the null hypothesis is true? And if that likelihood is very small, our assumption of the null hypothesis being true most likely would be false. If it's really unlikely for you to have gotten the data that you did, assuming the null's true, then maybe that assumption is false. So the smaller p-value we have, the more evidence we have against our null hypothesis, the more unlikely it is that your null hypothesis is true. How we found that likelihood was we used a test statistic, a z-score. We can interpret our p-value in one of two ways. We can think of it in terms of our sample statistics or in terms of our test statistic. There was a 3.59% chance that we would have gotten that sample proportion or bigger, or one bigger, if in fact the dice was fair. It was a 3.59% chance of us getting that sample proportion or one bigger if the dice was fair. Or we can think about it in terms of a z-score. There's a 3.59% chance that we would have gotten that z-score or one bigger if I gave you a fair dice. It was very unlikely for us to have gotten the results that we did if in fact I gave you a fair dice. So what we should be thinking about in the back of our head is, do you have enough evidence to say I gave you a fixed dice? Do you have enough evidence to say I cheated you? Well, maybe. I mean, that's kind of subjective, right? Yet, how much evidence do you need? You know, when you're sitting in a courtroom, and if you're a juror, you hear the defendant's case, you hear the prosecutor's case, they both made their cases, you're in the jury room. At what point do you convict them? I mean, different people require a different amount of evidence to come to some conclusion in their head. So the next step of a hypothesis test is going to be somewhat subjective in that now we need to make a binary outcome. Are you going to convict me or are you not going to convict me? Are you going to say I cheated and send me to jail, or are you going to say you didn't have enough evidence to say I cheated and not send me to jail? That is going to be step 4, determining if we have enough evidence or not.